Welcome to lecture 24. In this lecture, we will introduce a problem called topological sort on a directed graph. So there are two methods for solving this problem. Basically, the first method will try to give the vertices one by one in the correct sorting order in this topological sort. For the second method, we will apply DFS on the graph, and then finally, based on the result of DFS, we will give the correct order. So let's see what this problem is about. So sometimes directed graph can be used to indicate precedence among several events. So precedence means that several things has to be done before some other things. So for instance, this is an example of how do we wear our clothes. So there are some tasks that we need to do. For instance, we want to wear a shirt, we want to wear pants, we want to wear undershorts, belt, and so on and so forth. So for a logical person, so there should be some ordering among these events. So first of all, we should wear socks before we wear shoes, because otherwise the socks will not be inside and the shoes will not be outside. And for instance, we should wear a shirt before we are making our tie. And then there are also some other events like undershorts should be done before pants. And then after we wear the pants, then we should wear the belt after that. But then for some tasks, there should be no relative order between them. For instance, we can wear undershorts and we can wear socks at any time. They don't have any one that should be done before another one. So watch is something like an independent thing, so we can wear our watch at any time. So the arrows here indicates that which job or which task should be done before which other task. So this is called a precedence graph. So ideally, we want to find a way to order the vertices of this precedence graph such that whenever there is a directed edge from U to V, then U appears before V in the ordering. So in such a case, we can make use of this ordering to perform the tasks one by one, so that we don't need to worry that there is something wrong by the time that we perform a task, so that things that has to be done are not done yet. So whenever U is before V in the ordering, then we don't need to worry about there is an edge pointing back from V to U. Okay, so this problem is called the topological sort problem. The word topological comes from topology. It means structure. So here we are basically sorting the structure, which is the directed arrows in this graph. And in particular, so this is a particular outcome of this topological sort. So as we can see, we are giving orders of the vertices. So, and then we will see that for each directed arrow, it is pointing from always a smaller ordered node to a larger order node. So this is from 1 to 2. 1 is smaller than 2. This is from 6 to 7. 6 is smaller. So this is from 3 to 4. 3 is smaller. This is from 8 to 9. 8 is smaller. This is from 2 to 4. 2 is smaller. So we always, whenever there is a directed edge, it is always pointing from a smaller number to a larger number. Now actually we can easily see that if the graph contains a directed cycle, then we can never perform topological sort on the vertices of the graph. Yeah, because there is, for instance, because there is a directed cycle, there is always a back edge. No matter what we relabel the order of the vertices, there is always going to be some larger vertex pointing back to some smaller number. So you can try this at home to prove why this is correct, and it is easy to show this by contradiction. Now, when there is a directed cycle, we cannot topological sort. But on the other hand, we will show that if the graph does not contain a cycle, so in that case, we call it an acyclic graph, then topological sort is always possible. So we want to show this is true, and then we want to find out how we can efficiently perform this task. So let's leave it aside. Before we prove that, let us show a key lemma corresponding to the proof of that one. Okay, so this key lemma says, suppose that G is a directed acyclic graph. So we are assuming that the graph G does not have any directed cycle. So a short name for this directed acyclic graph is DAG, or simply we call it a DAG. Then we claim that if this happens, then some vertex of G must have integer 0. Okay, so we are going to show this by actually a constructive method. So let us start with any vertex. Let's call it V0, an arbitrary vertex V0. Now, if V0 has integer 0, then done. Then we have already shown that some vertex has integer 0. Okay. If it is not, then V0 must have some integer larger than or equal to 1. So that means that there is some vertex, let's call it V1, such that V1 has an arrow. V1 has a directed edge directly pointing at V0. So we will have V1 pointing at V0. So we continue the process. Now, if V1 at this moment has integer 0, then we are done, because now V1 is the vertex that we want to find. If not, then we will have some vertex V2 that points at V1. Okay, so this is the case. Now we can repeat this process. So if at this moment V2 has integer 0, then we are done. But if not, we can continue the process again and again. So we will get a sequence of vertices such that Vk points at Vk minus 1, Vk minus 1 points at Vk minus 2, and so on and so forth, then up to V0. Now, we claim that all the vertices here that we find in this sequence of vertices, they have to be distinct. Now, if not, so for instance, let's say V1 is equal to Vk. So let's say this is Vk, right? So if this Vk is actually V1, then what does that mean? So this is V1 and this is V1. So there's an edge pointing from V1 at this pointing from V1 to Vk minus 1. So by drawing this arrow in another form, so we are drawing this, there is an arrow drawing from V1 to Vk minus 1, then we will see that there is a cycle. And when there is a directed cycle, then this gives us a contradiction, because the input graph G, we assume that it is a DAG. So in that case, because it is a DAG, you cannot have a directed cycle. So it means what? It means that all the vertices has to be distinct. Now, if this is the case, then when we continue this process, either we must be able to find some vertex that has integer 0, but then if we do not, then we continue the process, but all the vertices that we see has to be distinct. So at some point, we will run out of some new vertices that we have not seen before. So at some point, this process must stop. And in that case, a vertex of integer 0 is found. So this shows that the key lemma is correct. So let's recall a little bit. So the key lemma says that for any DAG, there must be some vertex with integer 0. So this is the key lemma. Okay, now this key lemma directly gives us the reason why we can topological sort the vertices on the DAG. So to do so, suppose that we are given a DAG G, we can do the following. First of all, because it is a DAG, it has a vertex with integer 0. So let's find it. So let's call it U. In that case, we will output U. Notice that U does not depend on any vertex to be done before it, because its integer is 0. So we're done. Okay. And now we output U so that U should not be affecting any other vertices in the future. So we can now remove U and all its outgoing edges from the graph G. Now notice that after doing this process, the resulting graph is still a deck. It is because we are now taking away edges, so that previously when there are no directed cycle, after we take away edges, there should still be no directed cycle. So after removal of U and all the corresponding outgoing edges from U, then in that case the resulting graph is still a deck. So what we are going to do here is we are going to repeat this process to find another node. Because it is now a deck, we can now find another node with in degree 0, output it, remove it and its outgoing edges, and so on and so forth. In that case, the output vertices, we will see that it will form a topological sort order. It is because by doing this process, we will find out that, so imagine that the vertices, as we output it from left to right. Let's put the vertices along a line from left to right. Then we will see that at any time when we are removing a vertex and all its outgoing arrows, then the arrows will later be like pointing from left to right. So in that case, after the topological sort, all the arrows are pointing from left to right, and in that case, it agrees with what the topological sort is required, because all the arrows are pointing from a smaller value. Let's say when it is further on the left, it will have a smaller value, to a vertex with a larger value, with a larger order. Okay. Now, because of this, the previous method actually gives us a constructive method of topologically sorting the vertices. So this is actually our method 1. So let us analyze the running time of this method. So when we run this, we will need order v plus e time to compute the in degree of each vertex. So we can check the adjacency list and then record what is the in degree of each vertex by visiting the list, and then later we can find out what is a vertex that has in degree 0, and then we pick it. And for the next round, we can remove such a vertex and all the corresponding edges, and in that case we will repeat the procedure again and again. So each round we will spend v plus e time, and then there are only order v rounds, because each round we will output 1 vertices. So in that case, the total time is v times v plus e. On the other hand, we can actually do something smart so that we can make this faster. So this is a correct method, but then it is not the only way to implement this method. So what we are going to do, okay, next is we are going to keep an array A that tell us what is the in degree of each vertex at the current graph. Okay, so we will first initialize a list L, and then this, okay, so first of all, we will run this adjacency list and find out the in degree of each vertices, and then we will keep it at A. And after that, we will maintain a list L. This L corresponds to the vertices whose in degree is 0. What we are going to do here is that if a vertex has in degree 0, then we can actually output it at this moment. So we will check whether the list L has vertices with in degree 0. So if L is not empty, then we will pick any vertex U from L and then output U. Now by the time that we have output U, what we are going to do next is we will remove U from the consideration in the future, and also we will remove all the outgoing edges from U. So here what we are going to do to reflect this update is for each out neighbor V of U. So if there is an edge from U to V directly, V is an out neighbor, the time that we remove U will have the effect that we will make the in degree of V to be smaller, to be 1 smaller. So we will decrement the value of AV by 1, so to make the in degree of V 1 smaller. And by doing so, V may now become a node with in degree 0. So if AV becomes 0 at this point as well, then we can add, so there is a typo, so we can add V to the list L for future consideration. Is that okay? So in that case, after doing this process, we are not actually redrawing the graph again and again. So we will have a real-time update of the in degree of each node. So we will always pick a node with in degree 0, process it by outputting it and removing the corresponding out neighbors, the edges to the out neighbors, and then updating the in degree of the out neighbors. Okay, so this is a revised implementation of method 1. Okay, so if you go back here, line 1 and line 2 is just the processing of the adjacency list. So it can be done by linear time. Now the loop, so in loop 3 here, this is the loop, sorry. So this is the loop here for this line 3. Then we will repeatedly pick a vertex and then remove the edges outgoing from this vertex. Okay, then in such a case, then the time that we spend here is actually proportional to the number of edges that is connecting to the node that is being removed. So in such a case, then we can also see that this process, this loop in line 3, so this is a description of what it is done, but then the time that we spend in line 3 here is also V plus E in total, okay? So line 1 and line 2 takes V plus E, they are run once, and then line 3 is a loop, but then altogether the time that we spent is V plus E, so in that case, the total time is V plus E. So this is method 1. Okay, now method 2 is different. So method 1 will try to output the vertices one by one, and then method 2 will first run DFS and then output the vertices after running the whole DFS. So we are running the DFS, and then for illustration purpose, so we are running this and then also keeping track on the discovery time and the finishing time as we run it. So this is a certain input precedence graph that we have seen, and then let's apply a DFS on it. So for instance, we can start from shirt and then tie and then jacket and then go back and then go to belt and then go back and done for this round. So 1, 2, 3, and then go back 4, 5, and then we fly to this node. We have 6, 7, and then we go back at 8. Notice that we just need to get the relative order of this time, so we don't need the accurate account. So as long as the relative order is okay, so it's okay. So you can say 1, 2, 3, 4, 5, and then you can make it as 7, 8, 9. It's the same as we make it as 6, 7, 8, whatever. Okay. So after that, it's not done yet. So we still have some unvisited node, so we can continue the DFS process. And then here in our example, we will do the watch. So 9 here and then 10 back. And then 11 as socks, 12, go back 13 and then end as 14. 11, 12, 13, 14, and then 15, 16, 17, 18. And now after we have run the DFS, what we want to do here is that we look only at the finishing time. The larger the finishing time, the smaller in the topological sort order. So here, this is having 18, the largest finishing time. So we will mark it as 1. This is 17, the second largest finishing time. So we will mark it as 2. And 14 is, so we don't have 15, 16 because these two are discovery time, so we'll just ignore it. So the next one is 14. This is the third largest finishing time. So we will mark the topological sort order as 3, and so on and so forth. After we have done this, we claim that this will be a desired topological sort order. So we will find out that for each arrow here in this example, it is always pointing from a node with a smaller order to a larger order. So we will have the result like this. So topological sort in this way is very simple. We just run DFS, record the finishing time, and then sort it, and then what? And then the larger the finishing time, the smaller the topological sort order. So why does this method work? So first of all, we require that the input graph is a DAG. Okay. And also we have already studied the white path theorem. So let's examine each. So we are proving why this method works. So we now check for each edge, directed edge UV, whether by applying a DFS on this graph, whether we are always pointing from so here UV, right? We are pointing from a node with larger finishing time to a smaller finishing time. So we want to show that for each edge UV, f of v is always smaller than f of u. So in that case, f of u, so the u will have a larger finishing time, and then v will have a smaller finishing time. So here, why is it true? Okay, so why is it true? So if du is less than dv, if this is the case, there are actually two cases. Either du is smaller or dv is smaller. But if du is smaller, then u is discovered first, and then there is an edge uv, right? So by white path, v will be a descendant of u, and so we will have uv vu, and then uv vu, in that case f of v will be less than f of u. On the other hand, if v is having a smaller discovery time, so by the time that we perform DFS at v, we should not be reaching u at all, because otherwise there will be a cycle. So because graph G is a DAG, so there is no cycle. So by the time that we start visiting DFS at v, v has to finish before we can start visiting u. So in that case, the parenthesis theorem here will tell us that it is VVUU, and in that case, again, f of v will also be smaller than f of u. This shows us that by running DFS, the finishing time will automatically give us the correct topological sort order. Now, if you look at the implementation, so a naive implementation can be done by simply running DFS and then sorting the finishing time. So V plus E, and then also another time for V log V for the sorting. But actually, we do not need to do sorting, and actually, we do not need to keep the finishing time at all. So this cleverer method is we just use an extra stack S to help us. So whenever a vertex finishes its processing, we'll put it onto the stack. So in that case, in the end, the stack will contain the vertices, and then the ordering of the vertices from the bottom to the top will be according to the time that it finishes. The earlier that it finishes, the lower, or at the more bottom part, it will appear in the stack. So in that case, once we have obtained the DFS, and then the stack automatically will keep us the sorted order of the vertices according to their finishing time. So in that case, we don't ever need to sort the vertices. We don't ever need to record the finishing time. So altogether, the total time is just the same as DFS, which is V plus E. So that's all for the second method and also this lecture. Thank you.